Another vital criterion for a Boolean function to be secure is its nonlinearity, but please do not confuse the nonlinearity with the algebraic degree of a function. The nonlinearity of a function is defined as a minimal distance of this function to set of all linear and affine functions. And we said before that the distance can be expressed in terms of correlation. So if we change this distance function by the correlation function, we are going to have this expression, that is 2 to the power n minus 1 minus half of correlation between the function and all linear functions. If we take this 2 to the power n out of the minimum sign, we are going to have 2 to the power n minus 1 minus half of maximal correlation between function and linear functions and the maximal correlation between the function and affine functions. But as I said before, the linear functions and affine functions are at the maximal distance. So if the function is far away from a set of linear function, then it is going to come closer to affine function. So we can skip calculation of the correlation between function and the affine functions and stop with calculation of correlation between function and all the linear functions with the given number of input bits. But this task is going to be a bit hard task, because if we start counting all the linear functions, then we are going to have a linear function L1 which is equal to 0, L2 is equal to x1, L3 is equal to x2, L4 is equal to x3. Then we are going to consider all their combinations. L5 is equal to x1 plus x2, L6 x1 plus x3, and L7 x2 plus x3, and we have one more linear function with 3 variables, which is L8 x1 plus x2 plus x3. So this is the set of all linear functions with 3 variables, and to calculate the nonlinearity of function f, we need to calculate the cross correlation of this function f with all these L functions. That is, for each of these L functions we are going to construct its truth table and calculate the correlation function. Then we are going to construct a truth table for L2, calculate cross correlation, and this is a very time consuming operation, especially if the number of these variables increases. So to ease the calculation of nonlinearity, we should recall that the rows of Walsh-Hadamard matrix are truth tables of linear functions. So we can replace the calculation of cross correlation of a function with all linear functions with the Walsh-Hadamard transform of this function f of x. And we know that calculation of Walsh-Hadamard transform can be easily done by either butterfly algorithm or with the use of Walsh-Hadamard matrix. Then we just find the minimal value in the vector of Walsh-Hadamard transform, divide it by 2 and subtract the obtained value from 2 to the power n minus 1. So let's try to calculate the nonlinearity of this function. We have already calculated the Walsh-Hadamard transform of a function f, which was equal to 0, 0, 4 minus 4, 0, 0, 4, 4. So now let's try to calculate its nonlinearity. Nonlinearity of a function f is equal to 2 to the power 3, because we have 3 input bits, minus 1 minus half of the maximum of Walsh transform. Maximum of Walsh transform is equal to 4. So here we need to mention that the maximum should be taken by the absolute value of elements in the Volch transform vector. So then we have 2 to power 3 minus 1 is equal to 2 to power 2, which is 4, minus the maximal element of the Volch-Hadamard, which means that we multiply 1 over 2 by 4. And the nonlinearity of our Boolean function is equal to 2. So, as we can see, the Volch-Hadamard transform is very useful tool to calculate the nonlinearity of a Boolean function. In application of Boolean functions, there are two another vital criteria that should be satisfied, which are correlation immunity and propagation criteria. The correlation immunity means that there should not be any correlation of output bits, which are given by this truth table, with the input bits x1, with the input bits x2, and with the input bits x3. So, as its name suggests, we need to calculate the correlation of this vector with this vector first, then to calculate the correlation of this vector with this vector, and of this vector and this vector. So, if there is no correlation between the truth table of a function and each of these individual bits, then we say that the Boolean function is correlation 1 immune, because we are considering the correlation with only one input bit. In the same manner, we can try to calculate the correlation of this input with the combination of two vectors and so on. So let's see if our function given with this algebraic normal form is correlation immune. So for this algebraic normal form, this is our truth table. So let's calculate the correlation between the output and the x1 bits. The correlation is given by CF and x1, which is going to be equal to minus 1 to power 0. We are now calculating the polar form of the truth table. So next, minus 1 to power 0, minus 1 to power 1, minus 1 to power 1, this element, minus 1 to power 1, minus 1 to power 0, minus 1 to power 0, and minus 1 to power 1. We have listed all the elements in the truth table. In the same manner, we calculate the truth table for x1 elements. So we are going to have minus 1 to power 0, minus 1 to power 1, minus 1 to power 0, minus 1 to power 1, minus 1, minus 1 to power 1, power 0, and the last element is 1. So the calculation of polarized truth tables give us these two polarized forms, and the multiplication give us these elements. Summing up these elements, we obtain 0, which means that there is no correlation between the output bits and the first input bits. In the same manner, we are going to calculate the correlation between these output bits and the second input bits. However, instead of calculating the polar form of the truth table, we are going to use the property according to which if these two vectors are not correlated, then the bitwise XOR of these two vectors is going to be balanced. The same result was obtained here. For example, if we look at this vector, there is an equal number of plus ones and minus ones, and therefore we have a 0 as a result, which shows that there is no correlation. If we try to XOR these bits, we are going to have the equal number of zeros and ones. For example, these two bits would give us 0. XOR of this bit and this one would give us 1. 2 ones, this is resulted in 0. 3 1. XOR of this element with this element gives us 1. XOR of this element with this element will also give us 1. We have 4 ones, and XOR of this element is 0. XOR of this element is 0. So this rule always works. If the correlation between two vectors is equal to 0, then the bitwise XOR of elements will result in a balanced vector. Therefore, we can write down the function f, which is 0, 0, 1, 1, 1, 0, 0, 1, and x2, which is 0, 0, 1, 1, 0, 0, 1, 1. We XOR these results, which gives us 0, 0, 0, 0, 1, 0, 1, 0. As we can see, this vector is not balanced. We have 2 ones and 6 zeros. Since this vector shows us that there is a correlation between output bits and the second input bits out of 3, we say that the function x2 plus x3 plus x1 multiplied by x3 is not degree 1 correlation immune. And if it's not degree 1 correlation immune, there is no need to check this function for higher degrees of correlation immunity. So this is how we can calculate the correlation immunity of a function. However, it is really hard to calculate the correlation between the output bits and each of input bits, because as the number of input bits increases, we need to do a big number of calculations. Therefore, there is a second method to calculate the correlation immunity, where we can make use of a Volch transform. Actually, have a look to these input bits. These input bits represent the linear functions. If you remember, in the previous example, we write down all possible linear functions, and we had linear functions which is equal to x1, x2, and x3. So these functions are linear functions. And as we know, the Volch-Hadamard transform shows the correlation of the function with all linear functions. So to see if the function is correlation immune of degree 1, we can have a look at the values of Volch-Hadamard transform vector for weight 1 inputs. For example, this input is weight 1 because we have 0, 0 and just one non-zero element. For this vector, the corresponding element of Volch-Hadamard transform vector is 0. At the beginning of this example, we have already calculated the correlation between x1 and output bits, which showed that there was no correlation. And with the second bit, we obtained the correlation, which is actually equal to 4 from this example. So no need to calculate the correlations. We can just have a look at the corresponding elements of Volch-Hadamard transform vector. If we had this value of Volch-Hadamard transform vector to be equal 1, we would check the elements of Volch-Hadamard transform vector which correspond to weight 2 inputs. For example, this input is weight 2. Let me remind you that the weight of the bit sequences is calculated as the number of non-zero elements. So for this input we have -4, which says that the output bits is also correlated with a combination of bits x1 and x2. It is also correlated to combination of bits x2 and x1, since the corresponding element is equal to 4. However, this function is not correlated to the combination of bits x1 and x3, since here we have 0. However, this is not important because, as we saw in the example, the function is not correlation immune of degree 1. And the final measure that we need to calculate is the propagation criterion. A Boolean function f is said to satisfy the propagation criteria of degree k if f of x changes with a probability of 1/2 whenever one bit of the input is complemented. That is, for example, if we complement this input bit, then the half of output bits should change. How do we calculate if a function satisfies some degree of propagation criteria? So the main point here is that we need to complement one bit. For example, suppose that we are trying to complement the bit x1, then our first input is going to be not 0, 0, 0, but 0, 0, 1. For 0, 0, 1, we know that the value of the function is equal to 0. This is our f. Next, we complement the last bit in this string, then we have 0, 0, 0, and the last bit is complemented, and we know that with this input our function f is equal to 0 again. Next, we complement the last bit in this input string, 0, 1, the last bit is complemented and it becomes 1. So the output for 0, 1, 1 input is equal to 1. Next, 0, 1, it was supposed to be 1, but we complement the last bit and it becomes 0. For this input, the output is equal to 1. The next 1, 0, 1, and for this input, the output is 0. Let us divide this part by a line. So 0, 1, 0, 0, the output is 1. 1, 1, 1, the output is 1 here, and 1, 1, 0, for this input the output is 0. So as we can see, this f is just a shifted version of this f. Now we need to see if the half of bits has changed. For that, we can calculate the distance between this function, this output that we have obtained after flipping one bit in the input, and this truth table of the original function. Let us denote this shifted version by f tilde. So write down the f function itself, which was 0, 0, 1, 1, 1, 0, 0, 1. To see if the half of bits changed, let's XOR these bits. We have 0, 0, 0, 0, 1, 1, 1, 1. From the resulting XOR, we can see that exactly half of bits changed, which is clear from these 4 ones. So with the flip of the last bit, exactly half of output bits change. So these are operations that we have just performed. To see if the half of results changed, we use this XOR operation, and if exactly the half of bits changed, then in the result the half of elements is going to be equal to 1, which means that the resulting vector is balanced. So all we need to do is check if the resulting output is balanced. So now we have changed the x1 bits. Now let's try to change x2 bits. Then our result is going to be, so to do so, we write the resulting input bits after changing the bit x2. If we change x2 in the first input, then the input is going to be 0, 1, 0. The second input is going to be 0, 1, 1. Next is going to be 0. This 1 is changed to 0, and the last bit is unchanged. 0, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 1, 0, 1. So if we look at the values of f for corresponding inputs, then we know that for this input the value of f is 1. For this input the value of f is also 1. 1 for all 0 input, 0, 0, 0, 1 input results in 0, 1, 1, 0 input results in 0, 1, 1, 1 input outputs 1, 1, 0, 0 input after evaluation gives 1, and 1, 0, 1 gives 0. This is our f tilde. Write down f. F was equal to 0, unchanged f. 0, 1, 1, 1, 0, 0, 1. Calculating XOR of these two vectors gives us 1, 1. XORing 0 with 1 gives us 1, 1, 1, 1, 1, 1. We can see that this result is unbalanced. This means that not the half of bit, but all the bits have changed. Unfortunately, this reveals some weaknesses of our Boolean function. Therefore, we cannot say that this function satisfies the propagation criteria of degree 1. As we can see, when we change the second input bit, all the output bits have changed, and this means that our function does not satisfy the propagation criterion of degree 1. And since it does not satisfy the propagation criterion of degree 1, no need to try to change 2 bits and 3 bits. Again, as we can see, the calculation of propagation criteria degree is very time consuming. Therefore, we can again use the Volch-Hadamard transform vector. So, while calculating the propagation criteria in our example, we saw that each time we try to calculate the correlation of the function with its shifted version, which is the autocorrelation of a function. To calculate the autocorrelation of the function using Volch-Hadamard transform, we can take the Volch-Hadamard transform from this vector again. Let's try to do this. The Volch-Hadamard transform is calculated using the polar form of the truth table. So, to use the polar form of truth table, let us map zeros to ones and 4s to -1s. That is, all the values which are not equal to 0 are mapped to -1. 1, 1, -1, -1. Here I'm going to use a butterfly algorithm. In butterfly algorithm, to calculate the first element, we should add these two elements. 2. Extracting this element from the first element, we are going to obtain 0. -1 plus -1 gives us -2. Here we have 0. Sum of these two elements will give us 2. 1 minus 1 gives us 0. Here the sum gives us -2, and the difference is 0. So again, now we calculate these two elements, we sum these two elements, 0. The difference of these two elements is going to give us 4. This element summed with this element 0, difference is also 0. The sum of these two elements 0. 2 minus minus 2 gives us 4, and these elements give us 0. At the last step we sum these two elements 0. Sum of these two elements gives us 0. Sum of these two elements gives us 8. Sum of these two elements give us 0. Now subtracting this element from this element 0. This element 0. 4 minus 4 again gives us 0, and 0 minus 0 gives us 0. So here is the result of our calculation. We have all 0 vector except the third element. Using the same logic as we used in calculation of correlation immunity order, we can look at weight 1 inputs. Here this is the first weight 1 input, this is the second weight 1 input, and this is third weight 1 input. For the weight 1 input, where the x2 element is equal to 1, we have the value of resulting Volch-Hadamard transform being equal to 8, which is not equal to 0. That means that if we change the second bits, then not the half of the elements of output are going to change. This is the result that we have already obtained. If we try to check if the half of bits change when we change the input bit x3, then the result will show that exactly half of output bits change when we change the x3 input bit, because we can see that the resulting element of Volch-Hadamard transform is equal to 0. So according to the results given in this table, we can conclude that our function x2 plus x3 plus x1 multiplied by x3 does not satisfy the propagation criteria of degree 1. So in this lecture we have seen the calculation steps of basic Boolean function properties. The main security measures for Boolean functions are nonlinearity, high degree of propagation criterion, and high order of correlation immunity. And other measures that we have calculated are used to ease the calculation of these basic security criteria of Boolean functions. So in our next lectures we are going to use this criteria to show if a cipher is secure or not. The explanation of security measures for Boolean functions are also given in our text file together with all the calculation steps. So good luck with your homework. Bye.